In section 2.5, we take a look at graphing techniques and transformations. Um, let's start by talking about vertical shifts. Given a function f of x, if you took that function and added k to it, this is going to provide you with a vertical shift up k units. So again, this structure shifts the graph of f of x up k units. Similarly, if you were looking at the structure f of x minus k, this will be a shift down k units. For example, we just went through a variety of structures in the previous section. Suppose you're looking at the function x squared minus 3. You know what the graph of x squared looks like when you subtract 3 from it. You're going to take that base model function of x squared and shift that graph down 3 units. So your new graph is going to be down here like so. Similarly, let's take a look at the absolute value of x plus 2. We know that our absolute value function is that V-shaped structure, and we're taking this graph and shifting every single point up by 2 units. So the graph is now this guy. Okay, piece of cake. Those are my vertical shifts. We can also talk about horizontal shifts. Given the graph of f of x, the structure y equals f of x minus h is going to take the graph of f of x and shift it to the right h units. And similarly, y equals f of x plus h will shift the graph to the left h units. So again, considering the examples above, if you have x minus 3 squared, first of all, this guy looks like it's going to look like a parabola because you have that squared structure. And because you're subtracting 3 from those x's, you're going to take the graph and shift it to the right 3 units. So our original graph was y equals x squared. And we're going to take this graph and shift it to the right 1, 2, 3 units. So our new graph will look like so. Similarly, let's talk about the absolute value of x plus, let's say, 4. We know the base model absolute value of x looks like a v. And because you have a plus 4 here, you're going to move to the left 4 units. So your new graph is going to be over here. and look like so. Now, when you're talking about these vertical and horizontal shiftings, you can actually mix them together. For example, consider this extra problem. Let's go ahead and sketch the function x plus 2 squared minus 3. This guy is going to have a horizontal shift because you have that number added or subtracted to those x's, and it's going to have a vertical shift because it has a number added or subtracted to the general structure. For this kind of problem, it's not a big deal which one you do first, but just to play it safe, I tell folks to work their way out from the x when they're thinking about the order of operations for the shiftings. So I'll have you sort of focus on the horizontal shift first, and then the vertical shift second. You can actually do these shiftings one at a time to play it safe, to make sure you don't make a mistake. Again, right now, this one, odds are you wouldn't make any mistakes, but later on when things get a little bit more interesting, step-by-step process can really go a long way to keep us safe. So to get things started, again, I'll remind you that the base model of this function is quadratic, y equals x squared. If we were to consider only the horizontal shifting, then you'll be taking this guy and moving it to the left 2 units. And then if you consider taking that graph and subtracting 3 from it, then you'll be taking this graph and shifting it down 3 units. To ultimately getting a graph that looks like this. Let me say this. So knowing how to graph these guys can be really helpful. Suppose that you were looking at this function and they asked you to find the x and y intercepts. By knowing how to graph it, you can get some insight of what to expect. From my graph, I know that I should have at least exactly 2 x-intercepts and exactly 1 y-intercept. And also, I get a good sense of where those numbers are. Okay, continuing. Whenever you have... Actually, let me just entitle it. Vertical stretch or compression. So whenever you have a function that looks like a function that you're familiar with, f of x, let me write it this way, f of x, but you have a number in front of it, this is going to correspond to either a vertical stretch or vertical compression. When the value of c is greater than 1, we're going to have a stretch. When the value of c is between 0 and 1, we're going to have a compression. Consider the graph of y equals 3x squared. If we were to graph just y equals x squared, it might look like this. But that 3 is going to stretch it vertically, and it's going to make all of these points get bigger faster, so it will look something like this. So this is considered a vertical stretch. In comparison, if we have y equal 1/4 x squared, again, to start things out, y equals x squared will look like this. And that 1/4 is going to compress it. It's going to bring all these points closer towards the x-axis. So it's still going to be a parabola. It's just going to be smudged, right? Compressed. Now, don't get vertical stretches or compressions mixed up with horizontal stretches and compressions. So horizontal stretches or compressions look like a function you're familiar with, but instead of having the c in the front, they have the c in the argument right next to the x. So these are going to take your function and either stretch it or shrink it horizontally. So let's take a look with the following function. So let's say I give you the graph of f of x to look like a half circle of radius 1. So the graph of f of x looks like this. If you were to take that function and replace the argument with a 2x, this is going to correspond to a horizontal compression. So instead of going as far low and as far high as -1 and 1, it's going to compress it to -1/2 and 1/2. So imagine that you take this graph and you come in from the left and you come in from the right and squeeze it. If you were to do f of 1/2 x, this is going to take this graph and stretch it horizontally. So instead of starting at -1 and going all the way to 1, you're going to start at -2 and go all the way to 2. Okay, so again, when you're talking about horizontal stretches and compressions, when the value of c is greater than 1, you have a compression. And where the value of c is between 0 and 1, you have a stretch. This rule of thumb is opposite to what we saw for the vertical stretches and compressions. If you have a function and you create a new function by taking your original function and multiplying it by -1, you get a reflection about the x-axis. I think this one is going to sound kind of obvious. Suppose that I gave you the example -x². The graph of x² you're familiar with. It's just a parabola. And this negative is simply going to take these points and reflect them about the x-axis. So if you were to fold your paper along this line, those points will fall on this other side of the graph, and there's the graph of y equals negative x squared. That was a piece of cake, isn't it? Things get a little bit interesting when you start mixing things up. For example, let's say the following function has horizontal and vertical shifts and also some reflections. So for this extra problem, sketch y equal to negative x plus 2 squared minus 3. Think about what that will look like. So, which one do we do first? Can we do them in any order? You want to be careful here. Sometimes when you do them in different orders, you get different graphs, and we can't have different answers for this function, right? As a good rule of thumb, I tell folks to work their way out from the x, right? So here's the x. So right next to the x, I have this plus 2 that tells me that, hey, I have a horizontal shift. And right in front of this x plus 2 squared, I have this negative, so I'm going to do that second. And then I'm going to think about what to do with that negative 3. All right, so I know the base model. Y equals x squared. That plus 2, x plus 2 squared, is going to shift it to the left 2 units. So it will look something like that. The negative 1 in the front is going to take my current graph and reflect it about the x-axis. And then the negative 3 is going to take my current graph and shift it down 3 units. So your final answer is going to look like this. Done. So that was a reflection, or that was a problem that involved a horizontal shift, a reflection about the x-axis, and then a vertical shift. Let's talk about a horizontal shift. Or rather, I should say a reflection about the y-axis. So you'll be given a function f of x, and to reflect it about the y-axis, you would take your f of x and put a negative 1 in front of the x. For our last structure, for the reflections about the x-axis, the negative was in front of the function. For the reflection about the y-axis, the negative is inside the argument. For example, let's say that you were working with the square root function, and we're considering y equals the square root of negative x. So you know the graph of square root of x looks like this. And that negative in front of the x is going to take these points and reflect them about the y-axis. So if you were to fold your paper along that line, and when you fold the paper, you're going to ask yourself, where are those points going to land on the other side? And they will land over here. Let's try graphing this extra problem. Let's say y equals the square root of negative x plus 2 plus 1. So again, to play it safe, I'm going to tell you, hey, work out from the x. So do that one first, do that one second, do that one third. I know the base model of my function is the square root of x, so it's this guy right here. And with the x plus 2, I know to shift it to the left 2 units. So I have that guy right there. What would that negative do? If you were to fold your paper along this line, where would the points fall? So these points here would fall over here, and these points here would fall over there. And then finally, the plus 1 is going to take this graph and shift it up by 1 unit. So we get the following. Okay, so one step at a time, goes a long way on keeping us safe.